very much. And maybe, pardon?
The mic?
Oh, the mic. Do I really need that thing?
I think you don't need mic. Your voice is strong.
Generations of fishermen and seamen supposed to have voices to be heard over the storm, I guess. But I can make a little soft to modern technology.
It just makes it easier to record.
Yeah, sure. I'm just being a little facetious here. And if I then speak too loud, then please tell me to just remember that I do have a mic. Okay, so, well, this really has absolutely nothing to do with my talk today, except that I'm going to talk about hysteresis, and so I thought I'd have put in a little cyclic thing. So this is my yellow compressed air engine that I made a few years ago out of, it's all standard Lego parts. It's a design that's sort of roughly equivalent to a late 18th century, early 19th century steam engine with a walking beam. And this valve here, okay, here's double acting cylinder, there's a flywheel, the regulator there is just for entertainment, it doesn't do anything but go around. This is the valve, shifts the pressure from one side to the other of the piston. So of course the challenge with this, since it's a one-cylinder design, is to get past the dead centers. And that's what this flywheel does. Okay, so that's enough of that. If you are interested in my Lego stuff, then there's a link to it on my web page. And to find my web page, all you have to do is Google my name.
It's on your notes.
Pardon?
It's here also.
That's true, actually. So now, let's go where we're supposed to go. Okay. So the first two lectures then I told you about metastability somewhat in general, but illustrated with Ising models. And then yesterday I told you a bit about my simple-minded views of magnetization switching. And today I want to sort of go further on that and look at what happens with a simple kinetic Ising model type system when I drive it with an oscillating field. So instead of just flipping the field from one value to the other and see how the metastable state decays then, I'm now going to flip it back and forth. And it is work that's been done over many years with a number of people. Again, Mark Novotny is central to these collaborations. I will show some experiment by Andreas Berger and his group, which were analyzed by Dan Roth. That's about the oldest work. Scott Sides actually now works for a company here in Boulder. He was a grad student at the time. So, I'm actually going now to talk about finite size scaling studies of dynamic phase transition. So I'm going to use a lot of language from finite size scaling of phase transitions that's borrowed or stolen directly from equilibrium, although this is a far from equilibrium system. And so there's, of course, a number of finite size scaling of non-equilibrium phase transitions abounding. This is a little bit different from many, at least, that there's an explicit time dependence in the Hamiltonian, and in that sense that it's oscillating, both the ordered and disordered states can be seen as non-stationary, although you could argue that that they are stationary when you average in a certain way that I'll tell you about. Actually, this is a phase transition that was originally discovered numerically in simulations of a mean field, kinetic mean field model under an oscillating field. And I must say that I came into this essentially thinking that the earlier works were just baloney, and I wanted to show that there was no such thing as a phase transition in this system. Well, I was wrong. There is. So, here's the ingredients that I'm going to stir into my pot today. So maybe let's take it in the opposite, so order, the order that we talked about it. So, decay of metastable phase is what I have been talking about previously in my two talks. Then I'll use finite size scaling analysis of critical phenomena, and I'll some of you probably may know that from equilibrium statistical mechanics. For some of you it might be an introduction to finite size scaling. And then I'm going now to combine this with hysteresis. And hysteresis is actually, it was coined by a British professor by name Ewing back in the 1870s, while he was actually a visiting professor at the newly established University of Tokyo, where he was establishing, I think, the electrical engineering department. And it comes from a Greek word that means to be late, and that's essentially what hysteresis is. It's that you drive a system cyclically, but the system is too slow to completely follow your forcing. So it lags behind. And in that sense, even the Lissajous figures you see when you drive a harmonic oscillator is a form of hysteresis, although not so normally seen as that. Actually, hysteresis, it's now also important at very high frequencies, is in the sorts of high-tech devices that we have now, like the laptops and other computers and stuff. Back when it was first studied in the 1870s, it was really a very important aspect of the high-tech applications of the day, namely electric motors and transformers. Because hysteresis is essentially a measure of energy loss. So, the model I'm going to use today is, again, very, very simple. It's my old, sometimes known as the fruit fly of statistical mechanics, the Ising model. The only thing here is that I'm now going to use a time-dependent external field. Magnetization is the static order parameter. I'm going to be below Tc, such that in zero field there are two degenerate equilibrium states. Nothing new here. I'm going to use this as my stochastic dynamic. I'm going to use the Glauber dynamic, really for no particular reason. But actually we've also done this with other dynamics that I'm not going to talk about. Most recently with something we call the soft Glauber dynamics, when that was published only last year, or maybe even this year. So we keep coming back to this old horse and flogging it just a little more. Yes?
Can you give just like a 20 or 30 second explanation of what soft Glauber dynamics are?
Sure, I can do that. Let's see. Could I get some blackboard light, please? So here then, in the standard Glauber dynamic, I have, that's as it's written there, and there I have then the change in energy when I flip a spin is this, and the transition probabilities are based on the total change in energy. Right? Now I can decompose my change in energy into the change in internal energy and the change in field energy or Zeeman energy. So I can write this as delta, call it interaction energy, where if I have a spin here, say surrounded by, then this is just the change in energy when I flip this spin due to its neighbors. And then this is the change when this spin flips with respect to the applied field H. And so the soft Weber dynamics simply gives me the W SI S minus SI equals the standard Glauber, but using delta E interaction times the standard Glauber expression, but using just delta H.
Okay.
So that's all. It factorizes, and that actually changes the structure of moving interfaces in the system quite a bit, but it does not change the dynamic universality of what I'm going to talk about. Yeah. So that's okay. Again, reminding you of what I've been talking about before, where I'm going to use now systems that are large enough to be in the and with a large enough field amplitude that in an applied field of the strength of the field amplitude, these are in the multi-droplet decay region, so that I can use Abrami type theory to analyze it. And so remember then the nucleation rate per unit time and volume in a system in applied field H, that is this way, proportional to this, and then I have large supercritical droplets that grow at a constant velocity that's roughly proportional to the applied field. Those are the ingredients. Now I'm going to let H vary with time, and I'm really just looking at the adiabatic. Well, let me wait. So then, before we go there, just reminding you, then if I just change the field from, say, plus to minus and let it sit there, then the magnetization will go in time like this, going from plus to minus with this e to the minus t to the d plus 1 behavior, where this tau is the characteristic switching time that I can essentially will just measure by doing field switches. And just if I look at that, this function going, this is the typical Abrami curve, magnetization versus time for different field amplitudes. And actually here, we're going to work mostly at 0.8 Tc with an amplitude of 0.3, so that this curve would be sort of in between there. So here's, again, reminding us what things look like in the multi-droplet regime. Here's then a configurations following a field flip. We see at different coverages, and you see that I have supercritical droplets growing all over the system and then coalescing, which means that the metastable lifetime is independent of the system size. Yes, please?
So what is theta?
Pardon?
What is theta?
Theta here is the coverage. So it's the proportion of lattice sites occupied by equilibrium sites. Okay, now let's get to hysteresis. So now instead of just flipping the spin and the field and keeping it fixed, now I'm going to oscillate it. And in the adiabatic limit at least, I can then now say that my nucleation rate is going to vary in this form, where h now varies with time. It's quite common to use a sinusoidally varying field, and that's how we actually started out this work. The first work on this, and I think my second most cited paper, is a PRL with Scott Seitz, who I just told you is now working here in Boulder for a high-tech company. And but you can really do other things. You can use a sawtooth, something like this. You can use a shark's tooth or triangular wave, something like this. Or you can use a square wave, where your field just goes like this, and that actually is... Yes?
So, do you think the adiabatic limit is still valid for the case of a square wave or a sawtooth, where you're actually sharply changing your field at different points?
Yeah. It appears to be to the extent we have analytical results, they are in quite good agreement with the... So that's this. Then here, oops, okay. Now let's forget that theta on the previous slide was defined as the volume fraction or coverage. Here it is now defined as a scaled field period. So it's the half period of the field, which I have here called T1 half, divided by the metastable lifetime that I called tau. So that's going to be my, and I'm calling it theta because it will act as a temperature-like parameter in our simulations and analysis. All right. Now let me just show a very simple, motivating field. Here I have a two-dimensional kinetic Ising model in an oscillating field at Tc. Let's see, field amplitude, yes, field amplitude 0.3J. And I'm just showing here a very low frequency and a very high frequency. So at very low frequency, the system can follow the field. This is a sinusoidally varying, so essentially it says, well, the field is very weak, the waiting time would be long, and the system essentially sits in its metastable phase until you get to sort of roughly the dynamic spinodal. And then, as you can see, there's also some stochastic spreading here. Then when the field gets very strong, then it flips quite deterministically. So, and then the same thing. So I get this symmetric, rather squarish hysteresis loop. On the other hand, if I drive the system very fast, then it just doesn't have time to flip. So if I drive it much faster, then the lifetime, even at my strongest field, then typically it'll sit there and oscillate around the zero field result on one side here. And occasionally, as we will see, there will be a flip. But it won't. It will go essentially a random number of cycles between flips. And during that period, we get this sort of airfoil-like curve. So our question now is really, what's happening in between here? And I guess your first impulse, my first impulse certainly was, that there's probably nothing particularly interesting going in between, and I have some sort of continuous, gradual change from low frequency to high frequency. Well, that really turns out not to be correct. Well, here's just, before we get there, here's another view. Now I'm using a square field, and again, you see same temperature, same amplitude as I did before, and if I work at a low frequency, then you see the system reliably has time to switch during every period of the field, and I have this, so the square here, the dashed line are the field, the solid lines are the magnetization divided by the saturation magnetization. Yes?
You might point out that the temperature scales are very different, time scales are very different on the two plots.
Yes.
Those are small numbers.
Oh yeah, this is very true. This here, the time scale is 2,000 Monte Carlo steps per spin. In this one, this time scale is 200, so a factor 10. And then, so at the high frequency then, we have 10 times as high frequency, the period is much longer and much shorter than the lifetime, and therefore the system by and large does not have time to switch. It just oscillates near the saturation magnetization.
Quick question.
Yes?
On the slide that showed the hysteresis,
Yeah.
I assume both the x and the y-axis are functions of time here, right? You mean the function of time.
What? Here?
You mean m and h, the functions of time.
Yes. This is this h is a function of time, and so is m. So it goes. Let's see. Yes. So I'm cycling around this in this way, and here I'm cycling in this way.
I have one question
Yes.
about this plot too. When you reach the h value of 0.3 on the right side,
Yeah.
is the system in the equilibrium state?
Essentially, yeah. Oh, on the right side. Here you mean? No.
On the right
here.
side of the left plot. Yeah.
Okay, yeah. Here it has basically come to equilibrium. All right, so just let me give you a few quick simulation details here. The parameters, I'll be doing 0.8 TC. I'll be using a square lattice with system sizes between 64 and 512 squared. I'm going to use a square field. Now, why do I do that? Essentially for computational convenience, because if I use a continuously varying field, then I have to recompute my transition probabilities all the time, and that's very slow. When I use a square wave field, I only have two field values. I can just use two lookup tables for transition probabilities depending on which half cycle I'm in. The other reason is actually that it turns out that finite size effects are quite a lot smaller using a square field. Same universality class, we have done both, but if you want to push the envelope in terms of getting large systems and long runs and small finite size effects, the square field is the way to go. We measured the lifetime by just standard field reversal experiments to average 75 Monte Carlo steps per spin. System is large enough that the distribution around that is quite narrow. This is multi-droplet decay, and that our droplet separation, R naught, that we talked about before, is going to be about on the order of 10 lattice spacings. I already introduced the dimensionless field period, and the run lengths, as you can see, are quite long, from 3 to 15 million Monte Carlo steps per step, depending on where we are, the longest runs being close to what turns out to be a critical field period. Yes?
Have you considered different types of lattices?
Different size lattices?
Well, no, different types.
Types. No, we have not. Since it's a ferromagnet, I really don't expect much of a change, but no, we have not done triangular.
I'm just
or
wondering if the shape of the lattice might have some finite size effect.
Probably, although that when you look at the average order parameter, it's actually things look completely isotropic, which we're also at a relatively high frequency, and a very relatively high temperature, which smooths out the lattice anisotropy quite a bit. But yes, I would expect things to be somewhat more isotropic if I did say a triangular lattice, but I haven't. What we would like to do, but it is really still a big computational thing, and maybe not quite worth doing, is to do the three-dimensional model and really show that the transition, as we believe, will then be in the three-dimensional Ising universality class. That we haven't done, and it's until we do it. If we do, it's obviously free for the taking if anybody else. But please tell me so I don't reinvent the wheel if you do this in three dimensions. Just let me know. That's all I ask. Okay, so now we are going. Whoops, did I? Okay, yes. And then the analysis here, we're going to define ourselves now as a dynamic order parameter. And that is going to be the period average magnetization. So averaging the magnetization over a full period of the applied field. Therefore, when the period is long, then the system switches reliably, and so when I average the magnetization over a period, it goes to zero, right? The period average is zero because I always go through a full cycle. On the other hand, when I drive it very fast, then I don't switch by and large, and at least for long time periods, the system will just sit near one or the other of the equilibrium states and oscillate very much around very small amplitude around that. But at an intermediate frequency, and this is now very close to what I would I'm going to tell you is the equilibrium, is the transition, the critical one. We see this sort of wandering, where the dynamic order parameter wanders in a rather sort of random fashion, but quite slowly actually, back and forth. So essentially what you're seeing here is critical slowing down near the critical frequency. And if I were to lie to you and tell you that this is m of t for an equilibrium Ising model at temperatures high above Tc, well below Tc, and at Tc, I challenge you to call me on that line. Looks essentially the same. The reason it looks essentially the same, as we will show, is that it actually is the same in the sense that it's in the same universality class. Has the same critical exponents in terms of our theta, the scale period, as the equilibrium case has in terms of temperature. Here, I'm just looking now at, again, what is period average magnetization, but now locally. So at every field point, and here you also see my claim that things are pretty circularly symmetric. So here, this is the ordered phase, and what you see here, the way, is that, okay, I average over a period. Here, I have a cluster of the other magnetization direction that doesn't quite grow. It sits here and breathes and pulsates, and therefore you see that in the center, when the small droplet lives long enough, and then that you see the blue, you see the other phase here, and then it grows and shrinks and grows and shrinks, but it doesn't die here, and therefore I get these like, and then I see those that probably have just grown and died, or spent a very short time there at their equilibrium or whatever. At the disordered phase, we have this sort of disordered pattern of order parameters that are relatively close to zero. There are some areas that are positive, there are some areas that are negative, and they'll sort of switch around. At the critical point, I see this large shifting clusters where the order parameter is relatively close to one or the other of the equilibrium order parameters, and then some rather wide interfaces in between. So again, I would say, if I show this, maybe not for an Ising model because of these wide interfaces, but maybe more for a 5-4 field theory or something like that, at the critical point, this would be very similar.
Which part of the cycle are you showing us?
Which part of the?
Part of the cycle.
This is it's period or averaged again, but just with local resolution. The other one was just the full order parameter is just averaging the magnetization MOT, which is a space average over time. Here I have averaged each individual spin over the period. But so then if I average these again over time, then I will get my cube.
So the middle one, the critical one, looks quite different than critical fluctuations.
Well, I've just caught it sort of at the time where this is relatively close to zero.
I mean, if you were to take the same thing and zoom out to it with a bigger system size, would you see clusters at all length scales?
Yeah, you should. That's why we get scaling here.
It's just fuzzy because of the time average. It looks a little fuzzy as it's like in different force rings.
I think what Kinetic's meaning is that the order space is very much ordered inside domain.
Yeah.
It's not the same as the critical Ising model.
That's what I'm saying. It's an additional force ring.
There is enough.
Because of the time average.
But if you were to zoom out and consider much bigger system sizes, then you should.
I should see structure on, and also I see some structure here in smaller length scales. But yeah, and essentially now it's our finite size scaling that will show us that this is critical.
So what would hysteresis curves look like for each three cases?
Pardon?
What would hysteresis curves look like for each of the three cases? So for the left panel, it would look like a normal hysteresis.
Yeah.
For the right panel, it would look like that landscape. And for the critical,
here the hysteresis loop. Here the hysteresis loop would look like the standard hysteresis loop. Doing
a large period. Okay.
large period standard hysteresis loop. Here it will look like that pancake or airfoil shape. And here it would wander around. Yeah. Yeah, you would have something more or less pancake size, but wandering and sort of filling the whole space there. Okay, so finite size scaling, and I'm not going to give you a full introduction to finite size scaling theory of equilibrium phase transitions. I'm just, so for those of you who haven't seen that before, this can sort of serve maybe as a very, very quick introduction. So one of the best ways of finding the critical temperature in a temperature-driven second-order phase transition is to calculate what's known as the fourth-order cumulant ratio, or as the Binder cumulant. And it's essentially a way of calculating the shape of the order parameter distribution. Namely, if you're in the ordered state, this will essentially go to, in the ordered state where the order parameter distribution is essentially Gaussian around a non-zero mean field mean value, then this gives you about gives you two-thirds. If the order parameter is essentially Gaussian around 0, this will give you 0. And then at the critical point, you will have a crossing for different size systems. And so this has relatively small finite size corrections, so therefore it's a good way to find the critical point. And here you see I have a crossing about 0.91 or something like that.
By the way, just for the students, in the first week, in the third lecture by Steve Title, he was kind of introducing some finite size scales. So if you vaguely remember that, long ago,
yeah, that's a lifetime ago.
We'll have to worry about how many times.
It's like the undergraduate said, oh, I haven't seen an integral for a long time, like since 2 semesters ago. Yeah. Okay, so here we are. Actually, so here's my critical point. The other is that this is the crossing value of this fourth order cumulant is actually a universal number. And for the Ising model, it's 0.611 and lots of decimals. It's been measured very accurately numerically. Okay, another way of looking at finite size scaling is to look at the order parameter. So this is now, and so therefore if I go to the critical point and look here, you'll see as I make the system larger and larger, this will come in more and more steeply, and for an infinitely large system it would come in with a critical exponent theta of 1/8. So that's very steep, and it would be singular. Here then, for finite size scaling at the critical point, it scales with system size to 1 over beta over nu, where beta is the order parameter critical exponent and nu is the correlation length critical exponent. And here, as again, you see we do the finite size scaling, we get very good agreement with beta over nu for the Ising model. Here's a scaling plot that I based that one on, just plotting the average magnitude of the order parameter versus L on a log-log scale. We can also look at order parameter fluctuations, and here again we see something. So that's here I'm using really L squared times the variance of Q, and you see it has a peak that sharpens up and comes closer and closer to the critical point. Again, this would look very much like the zero field. This looks like the zero field susceptibility for an equilibrium Ising model, and doing finite size scaling, we again find very good agreement between the gamma over nu for this model in terms of this scale period, and gamma over nu for the equilibrium Ising model, where the control parameter is the temperature. And again, scaling plots, which show you that the agreement's pretty good. 1 over nu is the hardest one to find, but it's, yeah.
So, I mean, I'm looking at your scaling plots, and it seems that as you increase system size, you start to get more and more deviation from this nice scaling. And as somebody who's not worked in this field, I don't understand. I mean, if I was take this to the bulk system, would I?
No, it's essentially that.
Would I lose that scaling? Or?
No, I mean here actually this is done at the fluctuation maximum. Here I'm doing theta c. Essentially, what you're seeing is that the error bars go up. So I would here really, actually here, if you look gamma over nu here, it's quite close to the 1.75, the average value, and the last point, it falls well within the error bar. If you look at this one, my estimate's actually a little high, and so more likely the largest point here is going to give me a slightly better estimate if I had kept the largest point in and dropped the small one. Because for the small systems, I get very small error bars. Just because I can run long, and so therefore I tend in a weighted fit where I just weight with respect to the error bars, I'm actually tending to overestimate the small system results, or overemphasize the small system results because of their small error bars.
Yeah, I'm just wondering, going back to Kip's question, if you're going to lose this scalability as you get to larger system size.
We have never really seen that. We have good explanations, essentially, in loss of accuracy when we use very large systems. Good. Yep.
So it looks like the agreement is too good. That means the error bars are too big. Such a good agreement. Normally you'd want to see.
Yeah. Well, what I would say is rather that the error bars for the smallest systems are artificially small because of the high statistical accuracy there, so that I will take into account some of the corrections to scaling due to the small system size, because I'm sort of fooled by the high statistical accuracy. So there are I would say there are systematic errors for the small systems that I'm not taking into account properly because I am just looking at the statistical error bar. That's my interpretation. Yeah?
Should your scaling function...
Pardon?
Should your scaling function, all the exponents dependent on the temperature? If you change your temperature and change your field H0,
yeah.
Will the exponents be changing?
No. We have worked at different temperatures and field amplitudes, not at the same level of accuracy as we do here, but yes, we have checked. So this is essentially as long as you stay in well below TC. We have not tried to do this at TC, or we haven't done very extensive work. I think that would be quite complicated. But I'll also, in a moment, I'll show you order parameters, probability distributions that agree, again, extremely well with the equilibrium work. Yes?
Yes. This is essentially a dynamic phenomenon. how could you explain this resemblance with a static Ising model?
Well, there's a few ways of doing it. In collaboration with a good friend of mine at Kyoto University, Hirokazu Fujisaka, who tragically died way too young a couple of years ago, we did some analytical work, essentially showing that we can map this model onto a standard 5-4 field theory. And then the standard 5-4 field theory in 2 dimensions with noise, that we know is in the Ising universality class. There's also, just a second, there's also arguments, symmetry arguments, that say essentially that if you have a stochastic automaton with this Ising up-down spin symmetry, that's all you need in order to be in the equilibrium Ising universality class, and it doesn't matter that you're out of equilibrium. Yes?
So when you say you're comparing to Ising, what you're saying is you consider a static Ising model.
Yes.
And you're looking at finite time factor, and you're looking at distribution of order parameter as a function of finite, as a function of the size.
Yeah. Yeah.
So there's no time dependence at all in this Ising.
That's correct, yeah. Okay, so here...
Dynamic exponent 2 was the possible or just too hard?
We have not tried to find that yet. Or actually, George Cornes has some results. I don't calculating correlation functions, and I don't think he's ever published them. I think he went on bigger and better things when his students left or something.
That's another issue. I mean, even the static exponents look like the equilibrium model as the dynamic one.
I couldn't tell you. I think it will, but I don't know. Yes?
The scale function does not depend on the temperature, does not depend on the H0. Just because...
Sorry, can you speak a little louder? I can't hear you.
Just now you said the scaling function does not depend on the temperature and does not depend on the external field H0. But actually, the critical point, theta C should depend.
Depends on both. Yes. Yeah. No, I mean this is assuming that I do this at the critical point that depends on temperature and field amplitude. Yes. Yes.
Just to clarify Uma's question, he asked me about critical exponent z, for example.
Yeah.
This model, and your answer was that we would z to be what?
2 or whatever people think it is these days. Yeah. But I mean, considering that people are still discussing it for the 2D equilibrium Ising model, I'm not really sure I have the stomach to go after it for this model. Again, if you like it, feel free, but let me know so I don't go and do it sometime when I retire without knowing about it. All right. So here's now the order parameter distribution. Calculating the probability distribution of Q as a function of Q for different system sizes at the critical point. Here's the unscaled result. Here I am scaling with the Ising critical exponent beta over nu equals 1/8. You see very excellent data collapse. Not only that, and this really should be in blinking, this line here should be in blinking lights of a different color. That is a numerical calculation of the scaling function for the equilibrium Ising model. It is not on, and you see, it's falling right on. I can't even distinguish except when I look in logarithmic scale at the very, very tail of the distribution. So, okay. So, my conclusion is that this is in the equilibrium Ising class. Here is then just a reference to the work with Fujisaka-san. All right.
Just a question before we do the experiment. As you just go with the temperature to the critical temperature, your T just goes to 0. Correct?
Yes.
And then you just write in the model A critical point at that point. So the statement is that that is not an endpoint or something. It's an entire critical line that's described by the same universality.
Yes. Yes.
One more question.
Yes.
All these simulations with a fixed H naught for the
Fixed H naught
with
and fixed temperature.
Yeah. So on the relevant scales of the system, is that large or small? The value that you chose.
Pardon?
On the relevant scales of the system, is that H naught large or small?
It is large enough that the system is well into the multi-droplet regime for that temperature and that. So it's that it's somewhere between the dynamic spin-oval and what we call the mean field spin-oval, where the system is large enough to be well described by our Rame theory.
Does
Yes?
it mean that if you are in a single droplet model, the scaling will be different?
Then things are different, yes. And there's been a lot of discussion there. There's been claims that if you go to low enough temperature or small enough systems, you see a tricritical point and you see a first order transition. We did some very careful finite size scaling analysis for that, and that essentially we believe very strongly that is not the tricritical point, but it is essentially the crossover to the single droplet type decay, which is more like a stochastic resonance phenomenon. But yes, things do get different if we go into single droplet. Oh, yeah.
People look into Potts model, XY model, and this complex.
The Fujisaka group have done some XY model, higher spin Ising models. They've done a lot of work in this area. And, same conclusions, more and more complicated phase diagrams, many different disordered and ordered phases if you have high spin systems and so on. But that's okay. So now so far I can say that this transition really has been very well established for simulations. But what about experiments? Well, we are in collaboration with the group of Andreas Berger, who at that time was with Hitachi in California and now is in Spain and building his own institute there. My former postdoc, Dan Robb, who's now at Berry College as an assistant professor. The Hitachi group did, and we analyzed experimental data for a cobalt platinum 3 multilayer, which actually has a structure it's a good approximation for a two-dimensional Ising model with perpendicular anisotropy. Here's a sketch of the experimental system. Essentially, here, so we're using magneto-optic Kerr effect to measure the local magnetization. There's little demagnetizing phase. It's a very strong perpendicular anisotropy. There's relatively large grains. And so we also, here's actually a picture of this system on the scale of about 1 square millimeter during reversal. So you see very good circular. This definitely looks very much like the Ising model or Abrami's law during switching. Now, there's an experimental problem here, and that is in the simulations, it's very easy to set the field equal to 0. And of course we know for equilibrium Ising models, for the equilibrium transition, if you apply a field, we destroy the transition. Now we're experimentally in the situation that we can't really get the field completely to 0. So instead, we're trying to look at decay in a small applied field. It's called the bias field. So we just say we can't make the field 0, let's measure it and study how the system decays, and then we can do the simulations under the same conditions to compare. So that's what we do here. So on top here I see results for experiment. On the bottom I see simulation results. And I see 3 different, so I am, let's assume that we're slightly below or near criticality. The red line here is then oscillating near one of the metastable states. That's done in a weak positive field, so you would expect it to stay there. So I'm stabilizing so that that's actually say, now this is in the stable state and it'll stay there. In a weak negative field, that's this blue dotted line here, it should sort of be decaying but very slowly to the other, or it should just swim around if it's weak enough to be near 0. And if I put in a stronger negative field, then it should come quite quickly over to negative magnetization. So this is the experiment. Here it's the same data for the experiment, but on a much shorter time scale. You see here, oh, sorry, that's not true. This is period index, so it's the same data, but now just showing the period average magnetization per period. So here now this index I is not site like it was in the other work. Now it's the index of the period number. So again, you see that if I have a weak positive field, started out positive, it sort of will hang around there. If I do a very weak negative field, it will sort of hang around and then do that. If I do a stronger negative field here, then it will fall very quickly over to the other side. So here's the simulation result, exactly the same way of doing the experiment now. So that's close to the critical period. And again, you see, if I start it out on one side with a weak field that agrees with that, I did it pretty much oscillate that way. If I apply a weakly negative field, I'll sort of more or less sort of swim over to the other side. And if I apply a much stronger negative field, I'll drop over to the other side very quickly. So now then, I'll show you assembled data here. On the left I have experiment, on the right I have simulation. Here is my bias field, and this is my error bar for the bias field. And what I see here in the experiment is that as I go towards, we really just have our critical period at the very edge of the experimental results. The experiments were already taken apart by the time we got the data, and that's one reason. So we really have not been able to work at lower periods. But essentially what you see is that you go very sharply from strong negative to strong positive order parameter as we cross the zero bias field line. In the simulations, we see something very similar. Now, this behavior is more gradual than it is for the simulation. We believe that that is due to pinning in the experimental system. So we could also look at yes?
How are you comparing time in like seconds to time in Monte Carlo's, stuff? Like, I mean, if I just cut off the right hand side of the right hand plot, and it looks like the left hand plot. So how do I know what 1 second is in Monte Carlo kind of stuff? Well,
I don't a priori. I'm just seeing that I'm just comparing. So in that sense, yes, I don't really know whether maybe I should try to compress this scale a lot.
Right.
And therefore, if I allowed myself that freedom, yes, I could make this one look much more like this one.
Right.
Yeah. So we haven't done that, but yes, I could have taken that as one more free parameter, and then I could show you something that looked quite impressive. Maybe we're just not good enough salespeople, and that's why it took us 2 years to get this published. All right, here I can look at the fluctuations, and again, you see you see the fluctuation increase as we get down toward the smaller period. Here, actually, for the simulations, we were able to go a little bit below the critical temperature, and so we actually see a peak, as we would expect. Here, we just see that we're sort of getting into that peak region. Again, so we are talking about being doing more accurate experiments at lower periods. We haven't gotten there yet. Okay, now let's see. Oops, I am running over time, so I wanted to go a little bit back to some questions in non-equilibrium statistical mechanics, though, before I finish. So we can ask some there's some questions to be asked. Of course, you've already asked a lot of them, but let me ask some others. First of all, I haven't really identified a field conjugate to my dynamic order parameter in the simulations. It's reasonable to guess that that's a bias field, or the time average of the applied field, but we just haven't really established it. So yet, my answer will be yes, I can show that that's indeed the field, or proportional to the field I want in order to do finite size scaling in terms of field. The other question is, in the previous work, I blithely used the fluctuations in the order parameter as my proxy for the susceptibility, and I derived susceptibility scaling indices from that without really asking whether there is a fluctuation dissipation theorem relating my fluctuations to my susceptibility, defined as the derivative with respect to the effective field of my non-equilibrium order parameter. So this is now what I would set out to show that yes, it does indeed hang together. So therefore, I'm writing down now I'm proposing a fluctuation dissipation relation, and I want to see numerically whether it holds or not. I'll leave to the real smart guys to see if they can show it theoretically. So the MDH then, this is the definition of my susceptibility, finite size scaling, standard equilibrium thermodynamics shows this. It's just a consequence of the fact that the equilibrium partition function is a generating function for moments. And so does this hold? Again, we have shown numerically that it holds, but only really in the critical region, in the dynamic critical region. Okay, so here, as I say, I define this as my bias field. We've done this in the simulations just by adding a small constant field. Yeah, we're really into discussion time here. And so, doing that, I can show, indeed, for my numerical results, that the critical exponent delta, which for the Ising model is 15, is in very good agreement with the results. And maybe I should just skip through the rest here to give people time to ask questions. So, finite size scaling analysis, we make predictions of scaling functions. Here are scaling functions with fits that are in very good agreement, once again, with equilibrium Ising model, but now with the field as another degree of freedom that we can look at. And we can ask, now, do we have an effective temperature? And sort of yes, but then do we get too strong fields or periods that are too long, then we don't have linear relations. So as long as these relations are linear, then essentially we have an effective fluctuation dissipation theorem. We see some difference here at very low susceptibility of fluctuation, which essentially means very strong field. Here's our effective temperature. It's a function now of theta. It's more or less linear, but it's not the Ising critical temperature at there. Here's the expected slope, and here's some conclusions. I'll stop there.
Time for a few questions.
Yes?
So in the simulations you use global dynamics. Is there a way of writing a larger than equation based on maybe the fluctuation dissipation theorem so that the time really has a meaning in the simulations? Or
it should be possible. Now, I guess my question there would be whether I would be somehow cheating by using the fluctuation dissipation relation to define the Langevin noise. I would have to make sure I didn't bias myself there. That's my... It should be okay, but I would just... I feel one needs to think a little bit carefully about that.
This trivial comment I can make on it. It's
Yeah.
long in model A, which is that. So I think the hard part here analytically would be to see that the oscillating field maps into like a temperature-like variable. I think we can skip that, I'm not sure.
Yeah.
But as far as the noise is concerned, once you're there in model A and the noise is constant, so it doesn't contain any operators, whatever. It doesn't have to be the relaxation times kT. You can always rescale the fields to get there. Which is why at the critical point, the FDT is kind of recovered. So that in model E is easy to see. In model A is easy to see. So once you have your oscillations as a temperature line variable, that part is easier, and it's only applicable in the critical regime. Because, it's not true outside.
Yes?
For these smooth blobber dynamics that you wrote on the board behind you, soft, do they satisfy detailed balance or balance?
Yes, it does.
Okay.
It satisfies decal balance. Yes?
You said you had some mapping to the flat fourth theory?
Yeah.
That works in any dimension and
It works in any dimension, and that's why I feel pretty convinced that we should find three-dimensional Ising in 3D, but I admit we haven't done it. That is a question of faith at the moment, and I would love to see it done, and if I get someone who really would like to go after a question where we almost certainly know the answer.
Do you have a reference for that?
Yes, I do actually. I think I actually have it. No, let's see. I know I had. No, I must have skipped over it. Yes. Yeah, here it is. Okay. Here it is. Fujisaka, Tsutsu, and Rikvold, PRE 63, article number 036109, and that's 2001. Yeah?
Kawasaki dynamics. I'm interested. Has anyone done that? Conserved order parameter and the same business?
No. Well, if you have conserved order parameter, then the order parameter is indeed conserved, meaning
but you're still driving it.
I'm still driving it, but I would have to then I would need a different order parameter, because the magnetization then would be fixed at 0. So I would have to essentially use some measure of average cluster size or something. So again, the fluctuations I could look at, yes, but it would be interesting, but it would require some careful thinking again. But I think this is a fascinating area where you can sort of experiment with how far you can stretch the analogs between equilibrium and non-equilibrium phase transitions in many interesting ways. Yes?
Is your response function divergent as a quick response?
Yeah. Yes. In the infinite system, limited with divergent. Pardon?
Your response function defined based on the Q and H divergent as a quick response.
Yes, it diverges, but it's a finite system, so I have finite size scaling. So at the critical point, in order to see a truly infinite response, I would have to go to a truly infinite system. The peak of the response diverges as L to the gamma over nu.
More questions? Okay. Go ahead, we still have a minute. Yes.
Sure, I have a detailed question. I want to understand your phenomenal intuition. Can we understand in this way? In the high frequency, actually the adiabatic limit is not valid in this case, so you have the first transition rules. Transition.
The high. Well,
from the to the high frequency, can we understand? Because in the low frequency, you can have the adiabatic limit, but in the high frequency, you do not have the adiabatic limit. You cannot assume the adiabatic limit.
Mm-hmm. If the frequency gets very, very high, you can't. I would say that in the critical regime, I still can.
You still can?
Yeah. At least microscopically, but then
sounds like something to continue
Yeah.
discussion and the coffee break. Okay, so perfect timing. Let's take this.